Wish you all a very happy morning. Let us take up the next exercise. Exercise 1.3 of NCERT Standard 10. This exercise basically deals with proving of irrationality of numbers. How to prove irrational numbers. In Standard 9 you have studied that those numbers whose decimal expansion is neither terminating nor repeating are irrational numbers. Now in Standard 10 we are going to prove it. For proving irrationality of numbers we need a theorem. It states that if P is a prime number and P divides A, then P divides square of A also. So this is the theorem that we are going to use. If P is a prime number and P divides A, then P divides A square. The method that we are going to adopt in order to prove irrationality of numbers is method of contradiction. So we will understand how to use this method and this theorem to prove irrationality of numbers. So this is exercise 1.3 of NCERT, page number 14. The question is, prove that root 5 is irrational. How to prove root 5 irrational? So we are going to use method of contradiction. So we will say, if possible, let root 5 be a rational number. If possible, let root 5 be a rational number, then we can say root 5 is equal to P by Q. Since it is a rational number, so it can be written in the form P by Q, where P and Q are integers, Q not equal to 0. Also, we are going to take it in standard form, that is P and Q are co-primes. It means there is no common factor between P and Q other than 1. This is the most important part in the assumption, because the contradiction will be shown on this area only. P and Q are co-primes. So this forms the assumption part. Next, on squaring both sides, we will get square of root 5 as 5. This is P square by Q square. We are squaring on both the sides. From here we can say 5 times Q square is equal to P square. So you are expressing P square as a multiple of 5. So we can say 5 divides P square, therefore 5 divides P also. This is in accordance with the theorem that we have just discussed. 5 is a prime number and 5 divides P square, therefore 5 divides P. If 5 is dividing P, then I can write P as a multiple of 5. So, I am continuing it here. Let P is equal to 5C, where C is an integer. So we are taking C as any integer, and since 5 divides P, so I am writing P as 5 into some integer. Again squaring both sides. So what do we get? P square is equal to 5C whole square, that is 25C square. Now let us consider this statement as the first equation, where we are getting p square is equal to 5 times q square. So from 1, we can replace the value of p square here. We can write 5q square is equal to 25 c square, and we are writing this from 1. Divide both the sides by 5. On dividing both the sides by 5, q square is equal to 5c square. So c is an integer, c square is also an integer. So I have written q square as a multiple of 5. So you can say 5 divides q square also. So I am writing it here, this part. I am just erasing it. You can pause the video if you want to note. You can take a note of this. Now, we will say 5 divides q square, which implies that 5 divides q. So in the previous case, we have got 5 divides p, and now we are getting 5 divides q. So 5 is a common factor of both p and q. So 5 divides p, 5 divides q, it means 5 is a common factor of both p and q. This is a contradiction. This is a contradiction to our assumption. That P and Q are co-primes. P and Q are co-primes. We have assumed that there is no common factor between P and Q other than 1. But in the process, we have found that 5 is a common factor of both P and Q. So this results into a contradiction. So why this contradiction occurred? This contradiction is because of our wrong assumption. So we can say this is a contradiction to our assumption that P and Q are co-primes. This contradiction, or we can simply say our assumption is wrong. Why to write such a long statement? So we can say from here, since this is a contradiction to our assumption that P and Q are co-primes, so our assumption that root 5 is a rational number, root 5 is a rational number, is wrong. So this contradiction arises because of wrong assumption. So what do we conclude? So we conclude that hence root 5 is an irrational number. So we can say that root 5 is an irrational number. So this is a statement which is written in various forms. There are different ways of writing the same thing. That we are arriving at a contradiction because of our wrong assumption that root 5 is a rational number. This assumption is wrong. So what is the correct proof? Or we are concluding at root 5 is not rational, it is irrational. Because whenever we are talking about real numbers, either it will be rational or it will be irrational. If it is not rational, then it must be irrational. So here we conclude that root 5 is an irrational number. So in the same way, you can prove root 2 to be an irrational number, root 3 an irrational number, root 7 under root of any prime number can be proved to be irrational in the same way. So this was the first question of exercise 1.3. In the same manner, you can solve 1 by root 2, but for that, we can use the theorem directly. So I am solving question number 2 and showing you how to solve the second type of question by taking these root 5, root 3, root 2 as an irrational number. We are considering they are irrational and now we are proving it. The question is, prove that 3 plus root 2 root 5 is irrational. So there are different ways of solving the same question, but the conclusion is we have to use method of contradiction. We are assuming something wrong, so we are reaching at a wrong place. And then we are declaring that this is wrong because of our wrong assumption. So next question is question number 2. Prove that 3 plus 2 root 5 is an irrational number. Just now we have proved that root 5 is irrational. In your examination the question will be given as prove that 3 plus 2 root 5 is an irrational number given that root 5 is irrational. Root 5 irrational will be given to you. If it is not given and if it is of 4 marks, you need to prove that root 5 is irrational first and then you will prove this number to be irrational. So let us proceed. Let 3 plus 2 root 5 be a rational number. So we can say if 3 plus 2 root 5 is a rational number, then 3 plus 2 root 5 can be written in the form a by b, where both a and b belongs to the set of integers and b is not equal to 0. Now, we will keep the irrational number on one side and we will take all the other numbers to the other side. So we can say 2 root 5 is a by b minus 3. 2 root 5 is equal to b will be taken as LCM. So it is a minus 3b and root 5 is equal to a minus 3b by 2b. So clearly a and b being integers, b not equal to 0, a minus 3b is also an integer, 2b is also an integer, b not equal to 0, so 2b is also not equal to 0. It means the number obtained on the right hand side is a rational number. But it is given in the question and we have proved just now that root 5 is an irrational number. So how an irrational number can be equal to a rational number? This is not possible. So we find an irrational number is equal to a rational number. A rational number which is not possible. So this is a contradiction. This is a contradiction. And what is the cause of this contradiction? The cause of this contradiction is a wrong assumption. We have assumed 3 plus 2 root 5 as a rational number. This assumption is wrong. So after this you will write, this contradiction arises because of our wrong assumption. Hence, 3 plus 2 root 5 is not rational, it is an irrational number. So this type of question is generally asked in 2 marks, where it is given that root 5 is an irrational number and you have to prove 3 plus 2 root 5 as irrational. Proving root 5 as an irrational number generally asked for 3 marks. Sometimes it is also given in 4 marks question. It is one of the most important questions of this chapter, so you will go through it. So after this, hope you will be able to write it in the same manner as we have written it in the previous question. This contradiction arises because of wrong assumption and so our assumption is wrong. 3 plus 2 root 5 is a rational number. Hope you will be able to solve it. So with this, we come to the end of exercise 1.3 because question number 3 can be solved on your own. In the same way as we have discussed these questions, you can also solve exercise 1.3. Thank you.